Let's say we wanted to represent a general polynomial. Well, we could use series notation to represent a polynomial with no particular upper bound, and of course starting at 0, given some arbitrary coefficient. We can declare this to be our general polynomial, which would expand as such. If we have some coefficients c0, c1, etc., we can see that as we go and iterate along n, we expand out a general polynomial, and so on. Excuse me, that's supposed to be a 2. Mix this up. Expand out a general polynomial. And you can see we could represent any polynomial in this way, so long as we have the proper formula for Cn of the given case. But there's nothing to actually say that this will converge to anything in particular, besides our formula for Cn. A popular form you might have seen is the form of the Taylor series, where we choose Cn to be the nth derivative of a function over n factorial. So if we write this out this manner, this represents a Taylor series, but in this case a Maclaurin series of whatever f of x is, which would depend on f. So for example, e to the x has a Maclaurin representation of the following. Where the polynomial that is enumerated by this series notation converges to e to the x. And similarly, whatever function you could represent may converge to that function given that it satisfies some conditions. But broadly speaking, the tool of a power series gives us more freedom when working with differential equations because it allows us to make a guess of a solution that is extremely general. And for that, we are rewarded with a lot of differential equations which we can now solve with a series solution that we may have not been able to solve via other methods. But the trade-off comes in that we may not exactly have a closed form solution. And what I mean by closed form is similar to this. E to the x is the closed form of this series, which means that you don't have to actually evaluate the series term by term to see what it converges to. You can just evaluate e to the x. But it's not necessarily true that any series solution to a differential equation that we find will converge, or excuse me, will have a nice closed form that we would recognize. So to get a feel for it, let's take a look at an example. So let's take a look at the following differential equation. Y prime plus y is equal to 0. Well, starting off, this is actually a really simple equation. There's two ways to do it. Intuitively, you have to ask the question, well, what function, when you take its derivative, is the negative of itself? And there's a couple that could come to mind. Well, we know e to the x is a 1 cycle. That means the derivative of e to the x is e to the x. We know e to the minus x is a 2 cycle. The derivative of e to the minus x is minus e to the minus x, and then take the derivative of minus e to the minus x, and you get back to e to the x. We also know that this applies to sine hyperbolic and cosine hyperbolic, where they are each other's derivative. So the derivative of sine hyperbolic is cosine hyperbolic, and so on. And we know that sine and cosine are a 4 cycle. But we also know this applies to e to the ix, because I beginning at 1, you go 1, I minus 1, and minus I, and then back to 1. So e to the ix is also a 4 cycle. But in this case, if we take a look right here, e to the minus x, well, yeah, that seems like it satisfies the differential equation, so let's just say y is equal to c1 e to the minus x. Right, and we're done. But the point of the example is not to solve this particular equation, because we know methods by which to solve this. We can, you could do it by inspection like we just did, or if you'd like, you can do it by the method of constant coefficient equations, where you would find the characteristic polynomial. This would be m plus 1, so the root of the polynomial is -1, so e to the minus 1x is our solution, well, a constant multiple of that, and we're done. But that's not really the point of the exercise. The point of the exercise is to use a simple example to develop the theory. So let's instead try to find a series solution. So just like we did with constant coefficient equations, we are going to make a guess. So with constant coefficient equations, we made a guess that was something of the form e to the rx, or e to the mx, or e to some constant x. In this case, for series, we're going to make a guess that the function looks like a power series. Some power series, in fact, we don't have to be specific at all. Instead, we're going to be extremely general and say it's going to look like any power series that can be represented in this format. Or should I say, this is a power series, any expansion of this format. And again, this is going to give us a lot of freedom because we're essentially most likely going to be able to find a series solution for the equation because we're giving it really, really weak constraints. But the trade-off is we might not get a nice closed solution. So the way we proceed is we plug this in, just as we did with the constant coefficient equations. We plug this into our differential equation and see what rule it spits back out to us to tell us this is what needs to be true for the solution to be accurate. So let's plug this back in. Y prime, we're going to have to first find what y prime is. So y prime is going to be the derivative. When you take the derivative of a series, you have to remember that it is essentially shorthand for adding all these infinite terms. So every polynomial, every monomial is going to go down by the power rule. So we're going to have the sum still up to infinity. The constants are constants, which are unaffected by the derivative. We're going to have an n, and this is going to go down to nx, x to the n minus 1. But do keep in mind that the very first term of this is c0, is a constant, and a constant, when you take its derivative, is 0. So we do not need to include the 0th term in our derivative, so we shift our index up to n equals 1. Right? And notice if we plug in n equals 1 over here, we get x to the 0, which means we're just going to have a first term as a constant, which is what we expect. So now let's plug this in to our differential equation. So for brevity, I'm just going to copy them in. Equal to 0. Now, something you do not want to do is you do not want to treat these like integrals and take the constants out. That's not correct in this case because they're not integrals. First of all, there's no dx here, there's no delta x here. But second of all, even though these are constants, they're constants which depend upon the current iterator in the series. So c of 1 is not necessarily the same as c2, is not the same as c3. So to take cn or n out would be taking out iterator-dependent terms out of the series, which would change the value of the series. So we can't do that. Instead, what we want to do is we want to be able to use the fact that these terms are added together, these infinite series. So we want to make sure that these two are going up to the same term. In other words, we want to try to turn this n minus 1 into an n. Or we can turn this n into an n minus 1. It doesn't matter, but we can pick one. And I'm going to choose the n minus 1 because it's nicer to work with x to the n. So the way we do that is we recognize that n is just an iterator. If you've ever worked with programming, you'd be familiar with writing in Python syntax, for I in blah, blah, blah. You see, I doesn't have any special value. It's just a stand-in for an iterator. So what we can say is, n is cool, but let's make a substitution for our iterator. let's let our new iterator for this term right here, let's let our new iterator k be equal to n minus 1. And we can do that. We can substitute, but we have to substitute consistently. So let's substitute consistently. So let's look at the first term right here. N goes from 1, but k is 1 less than n. So k is going to begin from 0. Then c of n is going to be c of, well, let's look at our equation, add 1 to both sides, it's going to be c of k plus 1. Right? Because if we rearrange to solve for n, we get k plus 1. N, same way as it did for c, is just going to go to k plus 1. But now what we wanted, x is going to become x to the k. And now notice, like I said, k now is just a letter, right? So it's an iterator. It's not actually a value. So if we change it back to n for our own sake, for seeing clearly a relationship between these two, we can do that. So in fact, I will do that. I'll rewrite this with n, I'll refactor it with n, because the iterator can be any letter. So let's rewrite this with n really quickly. So the infinite series, the power series beginning at 0, from c n plus 1, n plus 1, and x to the n. And we can just copy the other side of this equation. A little big. Let's make it smaller. All right, make it a little smaller. There we go. Not the prettiest. So now that we have these two, let's write out a little bit and see if we can combine these in any way. So if we plug in n0 here, we're going to get c1 plus, c1 times 1 times x. So let's get, times x to the 0, which is 1. So we'll just have c1 plus, then we'll have c2 times 2 times x. So 2c2x plus blah, blah, blah. And now let's add these terms over here. Well, this is just going to be c0 to the times x to the 0th power, which is just 1. So that's going to be c0 plus c1x plus, and so on, right? Well, notice this is just a bunch of added terms, right? So we can go ahead and pair up the x to x terms, the constant to constant terms, and the x squared to x squared, x cubed to x cubed, and we're going to have a bunch of pairs of terms. Pairs of constant terms, pairs of x terms, pairs of x squared terms. We can then factor out the x. So we'll have a pair of constant terms with a factor of x to the 0 multiplied out, and we'll have a pair of terms associated with an x term, with an x squared term. But notice that we can write this itself as a power series representation. If that was unclear, let me write it out. We can write the sum of these two in the following form. Notice that the index of both is the same, and that's a requirement. The index begins at the same value, I should say. We can write this as c n plus 1 times n plus 1 plus cn times x to the n is equal to 0. Now, notice in this case, for example, cn plus 1 n plus 1 plus c would be like pairing c1 plus c0 and then 2c2 plus c1, etc., and so on. You'd see that it always matches the appropriate x power term. So now that we have this relation, we have to also recognize the fact that in an equation, or at least with the equations we're working with, if ab equals 0, one of these is always going to have to be one of these is always going to have to be 0. In the same way, if the series expansion of this term is equal to 0, that means either this term is always 0 or this term is always 0. Well, we know x to the n can't always be 0. In fact, x to the n is probably not going to be 0 for any value that's positive because you're adding terms. So that means this recurrence relation, or rather this sum of, I spoke ahead there, this sum of constant terms of coefficients has to be what's equal to 0 at all times, right? And just to clarify, if x is 1, for example, at x equals to 1, well, you're going to get 1 plus 1 plus 1 plus 1 plus 1, blah, 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 which is not 0. So we know that this over here has to be what is equal to 0. So we can set it as such. And now is the proper time for that word to come in, recurrence relation. This forms something called a recurrence relation, whereby we're defining a following term based on a preceding term. A common recurrence relation you may be familiar with is Fibonacci sequence, which kind of looks like this, where a term is determined by the sum of the previous two terms. That's essentially what this means. So just like that Fibonacci relation, we have a different recurrence relation right here, not necessarily the Fibonacci one, just a different one. So let's rearrange this to express it in terms of Cn plus 1. So let's subtract, if we subtract Cn from both sides and then divide by n plus 1, and again, n plus 1 cannot be 0 because n begins at 0, so the smallest this can be is 1. We're going to get that Cn plus 1 is equal to Cn over n plus, with a negative sign on the front. Now this gives us our general recurrence relation, but the problem is that we want a more closed form, or at least we want to take a look and see if we can find a nicer form for this recurrence relation, right? So the way to do that, really simply, is to just generate a few terms manually and see if you can see a pattern. So let's do that. Let's begin with C of 0. And notice C0 is kind of the lowest we can do. Remember, C0 in this case means that n is negative 1. That's not in our range even. So let us treat C0 as our constant. Because recall, in the solution that we are probably going to end up having, there is still a constant. So let's call C0 our constant. Now C1, remember C1 occurs when n is 0, because this is C of n plus 1. So if n plus 1 equals 1, then n equals 0. Then we know that C1 is equal to, well, if n is 0, this is going to be minus C0 over 1. So then C2 is going to be minus C1 over n plus 1. n plus 1 is now 1 plus 1, so 2. But we know C1 is equal to minus C0 over 1, so this is going to be equal to C0 over 2 times 1. Now, if you can see the relation already, that's good. But let's do one more term. Let's get C3 in here. C3 means that n is 2. So we're going to have minus C2 over 3, which is going to be minus C0 over 3 times 2 times 1. Right? So you notice that after each iteration, the number up here, or rather the number in the denominator, increases by a factor which is precisely the same as n. More precisely, we can say that this is equal to minus C0 over 1 factorial. This is equal to C0 over 2 factorial. And this is equal to C0 over 3 factorial. Do keep in mind the negatives here. So we're going to say that we have found the pattern. We know the pattern is that it alternates minus plus, minus plus. It always has a C0, and the denominator is always a factorial that is exactly n, right? Because if we're on C3, it's 3, C2, it's 2. So Cn here is equal to, well, let's first deal with this plus or minus. If we wanted to represent alternating positive and negative numbers in a series, one way we can do that is with the following to the n. If you imagine -1 to the 0, that's always 1. -1 to the first is -1. -1 squared is 1. And so on and so forth. It alternates back and forth between 0 and 1. Excuse me, between 1 and -1. So let's just do a quick sanity check. 1 should be negative, and to the first power, -1 to the first power is negative, and it is negative. But 2 should be positive, and it's positive. We already decided that it was going to be n factorial down here, so we make it n factorial. And one more factor we're missing is, of course, c0. So we've solved for Cn. But in fact, that means we've solved our problem. Because remember, the unknown in our original guess was right here. Was this Cn? The expression for the constant. That is missing for the coefficient, excuse me. But we found our coefficient. We know what it is, or we know what it is given a specific iterator. So let's write it as such. Y is equal to the infinite sum from n equals 0 of -1 to the n over n factorial times c0 times x to the n. Wonderful. And you could leave it like this, and you could even evaluate it like this. If you were doing some work in physics or math or wherever, and you just gave up with trying to search through your textbook and find the specific method, and the online calculator didn't work, and you didn't want to ask anybody because you just didn't want to say you didn't know how to do it, so you did it like this, which good job, and you plug it into your Python, you're probably going to get the correct solution for whatever number you plug in for x, so long as it converges at that point, which we'll worry about later. But there's a nicer way to represent this. But in general, that's not true. In general, there's not a nice way, a closed form to represent your series. In general, this is where the problem stops. But because we are fans of Taylor series, we are great fans of Taylor series here, and Maclaurin series specifically, we can come back up right over here and steal this and take a look at it. Right? So if we inspect this, kind of looks similar, doesn't it? It's got the n factorial down there, it's got the x to the n, it has the c0, but c0 is just a constant, and it's a constant that does not change with n, so in this case, we can even take c0 and drag it out of our little box. c0 can come out, but not c sub n. This looks extremely similar to e to the x. In fact, if we take e to the minus x and plug it in for x, what are we going to get? We're going to get this infinite sum. 1 over n factorial is unaffected, but what is affected is the x, minus x to the n. Well, this is just the same thing as -1 to the n times x to the n. But then if we look up here, that's what we have. So this is actually equal to c0 e to the minus x. And we're done. That is the series solution to our problem, and we have confirmed it by solving our problem in 2 different ways. So we know that this is a valid solution, and it's a solution that does what we expect, right over here. See?